Beneath the tranquil veil of the night sky lies a universe brimming with horrors beyond human comprehension. In the vast spectral void of the cosmos, there dwell entities of such bizarre and daunting nature, they appear as though conjured from the darkest corners of a cosmic horror tale. Envision forces of unfathomable power, capable of extinguishing planets and distorting the very fabric of time. Within the cosmos's deepest shadows, where even light hesitates to venture, rest secrets that send shivers down the spine of the universe itself. Within the infinite expanse of the cosmos, when a star significantly larger than our sun exhausts its nuclear fuel, it marks the beginning of one of the most extraordinary phenomena in space. Imagine a star that is significantly bigger than our sun, possibly more than 20 times as massive. These celestial giants consume their nuclear fuel at an astounding rate, living long and dying young. One of the most amazing occurrences in the universe, a supernova explosion that outshines entire galaxies, signals their downfall. Following this star explosion, the residual core must eventually confront its demise. It starts an incredible collapse under the force of its own gravity if it is huge enough, usually more than 3 times the mass of the sun. This collapse is so intense that the core's matter crushes into an infinitely dense point, known as a singularity. Around this singularity forms the event horizon, a peculiar boundary conceptualized by astrophysicists like Kip Thorne in Black Holes and Time Warps. This is the point of no return, where the gravitational pull becomes so overpowering that nothing, not even light, can escape, thus giving rise to a black hole. These stellar black holes are just one category in the black hole family. The universe also harbors supermassive black holes lurking at the centers of galaxies, including our own Milky Way. These are staggering in size, ranging from millions to billions of times the mass of our sun. Their formation is a subject of ongoing research, with theories suggesting they might originate from the collapse of enormous gas clouds or from the mergers of numerous smaller black holes over cosmic timescales. Supermassive black holes play a crucial role in shaping their host galaxies, influencing everything from star formation to the evolution of the galaxy itself. Venturing beyond the colossal supermassive black holes, we encounter the intriguing intermediate black holes. These cosmic entities, with masses akin to a cluster of stars, between a few hundred to several thousand solar masses, may arise from the merger of smaller black holes or as remnants of gigantic stars, offering crucial insights into the growth patterns of black holes. Moreover, the mysterious primordial black holes, which are thought to have formed soon after the Big Bang, may be present in the cosmic landscape. These might be as big as a mountain or as tiny as an atom, and they might provide light on long-standing mysteries concerning the origins of the universe and the nature of dark matter. In the realm of theoretical physics, micro-black holes present a fascinating possibility. These minuscule entities, possibly just a fraction of a millimeter across, yet with masses comparable to large asteroids, are hypothesized to form in high-energy environments where quantum and gravitational forces intersect. The search for these tiny black holes challenges our understanding of the quantum realm and could revolutionize our grasp of the fundamental principles of space and time. Investigating a black hole's anatomy reveals a world where basic physics is stretched to its utmost. Traveling into a black hole transports us to a place of cosmic terror and incomprehensible wonders. The event horizon acts as the eerie threshold of this abyss, a sphere of ultimate darkness where the gravitational pull becomes so immense that not even light can flee its grasp. This boundary, unique for each black hole and defined by its Schwarzschild radius, marks a transition into a realm where conventional physics loses its footing. Beyond this threshold of no return, the environment becomes increasingly hostile and bizarre. Space and time, those fundamental fabrics of the universe, undergo severe distortions. Imagine time stretching and slowing down, a phenomenon known as time dilation, and space being twisted and warped under the extreme influence of gravity. Time dilation is a phenomenon from Einstein's theory of relativity, where time passes at different rates for observers in different gravitational fields or moving at different speeds. Near a massive object like a black hole, or at high speeds close to the speed of light, time slows down compared to an observer in weaker gravity or at rest. Moving further into the depths of the black hole, the journey is rife with theoretical terrors. Paths once straightforward now inexorably curve inward, compelled towards the singularity. At the singularity, an area of nightmarish proportions, matter is believed to collapse into an infinitely dense and infinitesimally small point. Here, in this heart of darkness, the very concepts of space and volume lose meaning. Traditional physics, including the towering theories of Einstein, falter in explaining what happens within this singular point, making it one of the most enigmatic and terrifying concepts in astrophysics. Circling the event horizon is the accretion disk, a maelstrom of destruction. Here, gas, dust, and fragments of devoured stars heat to unimaginable temperatures, spiraling violently into the black hole. This swirling vortex emits high-energy radiation, a ghostly and powerful glow that serves as a testament to the black hole's insatiable appetite. It's a chaotic, hellish environment where matter is shredded and energy is unleashed in a cosmic spectacle of destruction. In the case of rotating black holes, the surrounding ergosphere adds another layer of dread. In this bizarre region, space-time itself is dragged in the direction of the black hole's rotation. The boundary of the ergosphere is not a fixed shell, but a dynamic, fluid-like surface, distorting reality in a way that challenges the very nature of physics as we know it. In the middle of these scary characteristics, the idea of Hawking radiation adds a subtle twist. Proposed by physicist Stephen Hawking, this theory suggests that black holes can emit radiation due to quantum effects near the event horizon, hinting at their slow but eventual evaporation over eons. This radiation, while faint, stands as a beacon of quantum mechanics in the overwhelming darkness of black hole physics. Although black holes' all-consuming nature suggests a cosmic threat, their impact goes much beyond simple annihilation. Black holes can act as cosmic catalysts. When a black hole pulls in matter, it doesn't always devour everything. Some of the material gets accelerated and ejected back into space at nearly the speed of light. The intense radiation from the accretion process can also affect the interstellar medium, the gas and dust filling the space between stars. This can lead to either the suppression or triggering of star formation in neighboring regions, playing a subtle yet profound role in the life cycle of galaxies. In the bustling centers of galaxies, black holes can induce dynamical friction, a process where the gravity of the black hole interacts with nearby stars and gas. This friction can cause stars to migrate to different orbits, or even be ejected from the galaxy at high speeds, altering the very architecture of their galactic homes. Another fascinating aspect is the role of black holes as cosmic recyclers. By breaking down matter to its fundamental constituents, they contribute to the cosmic cycle of matter, dispersing elements that can later be part of new planets and stars. Furthermore, black holes can change how electromagnetic waves propagate, which can have an impact on how light and radio waves are transmitted throughout space. This may result in events such as gravitational lensing, a phenomenon that gives us a distorted or magnified vision of far-off objects by bending light from nearby stars or galaxies around a black hole. Some scientists propose a mind-bending theory, suggesting that our entire universe could exist within the event horizon of a massive black hole. Known as the black hole universe hypothesis, it speculates that the singularity at the center of a black hole might connect to another universe, giving rise to the possibility that our reality is just one chapter in a cosmic multiverse. It serves as a chilling reminder of how the black hole may bend space, time, and our understanding of the cosmos, inspiring wonder and anxiety in humans in the face of these cosmic mysteries. When we think of planets, We often picture the familiar, orderly orbits of our solar system, from Mercury's swift path to Neptune's distant loop. A group of intergalactic vagrants, planets without a star to call home, exist outside of the peaceful orbits that make up our solar system. These are the rogue planets, lone wanderers lost in the great emptiness of the galaxy, isolated and exposed in the enormous fabric of space. Unlike the familiar planets of our solar system, rogue planets do not orbit a star. Instead, they drift freely through the galaxy, unbound by gravitational ties to a solar system. These interstellar drifters range in size and composition, from gas giants larger than Jupiter to rocky worlds akin to Earth. They roam the vastness of space in solitude. Devoid of a star's warmth, these planets are realms of intense cold, where the lack of sunlight transforms their surfaces into frozen wastelands. Imagine landscapes dominated by ice, possibly with towering structures akin to mountains and valleys, all sculpted by the relentless chill of space. These planets, cloaked in darkness, could feature surfaces where even atmospheric gases become solid, creating surreal, icy formations. The absence of light renders them invisible to the naked eye, painting a picture of ghostly worlds wandering unseen through the galaxy. Their true appearance, hidden in the shadows of space, leaves much to our imagination, hinting at a variety of unearthly terrains and frozen vistas, far removed from the warm, lit conditions of planets like Earth. Rogue planets lead a nomadic existence. Some were formed in the early chaos of their home systems and flung into space, while others may have formed independently in the galactic void. What makes these celestial nomads so frightening? It's their stealth and unpredictability. Shrouded in darkness, they travel unseen, their paths unknown. For years, rogue planets were mere theoretical entities, speculated by astronomers, but not yet seen. These hidden worlds were thought to exist in the cold expanse of space, far from any star's light. The breakthrough came with the first observational evidence. Using techniques like gravitational microlensing, astronomers began to spot these elusive planets. One of the first identified rogue planets was PSOJ 318. 522 discovered in 2013. It's a young, Jupiter-like world floating alone in the vastness of space. Rogue planets, hidden in the cosmic shadows, present a unique challenge to astronomers. How do we detect these elusive wanderers that shine with no light of their own? Unlike stars or planets orbiting a star, rogue planets don't emit significant light, making them virtually invisible against the vast backdrop of space. One key method we use is gravitational microlensing. This phenomenon occurs when a rogue planet passes in front of a distant star, bending and magnifying the star's light. Microlensing is a powerful tool. It allows us to infer the presence of a planet from the way its gravity distorts light, acting as a cosmic magnifying glass. A question comes to mind when we gaze out into the expanse of the cosmos. How many rogue planets are there in our galaxy that we are unaware of? Since rogue planets do not emit light of their own, counting them becomes a formidable challenge. This lack of luminosity renders these celestial wanderers nearly invisible, complicating our efforts to estimate their numbers in the vastness of space. Yet, what we've learned so far is astounding. Some astronomers suggest there might be billions, perhaps even more rogue planets than stars in our Milky Way. Research, including studies using gravitational microlensing, points to a surprising abundance of these interstellar objects. They could be lurking in every corner of our galaxy. If true, this means that rogue planets are a significant, though hidden, component of our cosmic environment. They play a far greater role in our galaxy's makeup than previously imagined. One of the most terrifying risks they pose is a direct collision with Earth. Though the odds are astronomically low, the impact of such an event would be catastrophic, potentially ending all life. We've witnessed the destructive power of smaller celestial bodies, like the asteroid that contributed to the extinction of the dinosaurs. The immense gravity of a rogue planet passing by could disrupt Earth's orbit, triggering catastrophic climate changes or pulling us out of the habitable zone. The disturbance isn't limited to Earth. A rogue planet's path through our solar system could wreak havoc, destabilizing orbits and potentially flinging other planets or moons out of their paths. Current technology makes spotting these interstellar intruders a challenge. We rely on indirect methods, which may not give us enough warning to react or prepare for a potential encounter. In the cosmic narrative, the aftermath of a supernova is often associated with the birth of black holes, but that's not always the case. As remnants of supernova, they present a different path in the cycle of stellar evolution, one that challenges our understanding of matter and gravity. Contrary to the common path leading to black holes, not all supernova result in these dense, light-swallowing giants. Stars with a mass lower than the threshold required to form a black hole take a different route. As they explode in a supernova, their cores collapse to a point of extreme density, but instead of becoming a singularity, they form neutron stars. This remarkable transformation results in some of the densest matter in the universe. Imagine a sphere just 12 miles wide, no larger than a city, yet harboring more mass than the sun. This is the domain where a single teaspoon of matter weighs a staggering 1 billion tons. Picture the Great Pyramid of Giza, not sprawling across the desert, but compressed into a grain of sand, or all the cars on Earth condensed into a thimble. Such is the unfathomable density of these remnants of supernova explosions. But their strangeness doesn't end there. Their gravity is 1,000,000 times that of Earth's, so intense it warps space, bending light around them. These stars are not just dense, they are also incredibly fast spinners, some rotating hundreds of times per second, emitting beams of radiation from their magnetic poles like cosmic lighthouses. These beams, coupled with their rapid rotation and extreme magnetic fields, unleash torrents of electromagnetic radiation. Their surface, made of iron atoms crushed to the brink of physical possibility. Beyond their astonishing physical properties, neutron stars play a pivotal role in the cosmic narrative. These stellar remnants are not just endpoints of star life cycles, they are key players in some of the universe's most dynamic events. These dense dwarfs often exist in binary systems, gravitationally bound to a companion star. In these systems, they can act like cosmic vampires, siphoning material from their partners. This process can lead to spectacular X-ray emissions, visible across vast interstellar distances, offering us a window into the high-energy processes of the universe. Perhaps most intriguing is what happens when two neutron stars are locked in a gravitational dance. As they spiral towards each other, they warp the space around them, creating ripples known as gravitational waves, a phenomenon predicted by Einstein, but only directly observed a century later. These gravitational waves carry information about their origins and about the nature of gravity itself, providing a new tool for astronomers to study the universe. The climax of this dance is a collision, a momentous event that unleashes a kilonova, an explosion so bright it briefly outshines the entire galaxy. These kilonovas forge elements heavier than iron, including gold and platinum, scattering them into space. Thus, neutron stars are not just theoretical curiosities. They are celestial forges where elements essential to life and to our very existence are created. In this way, these stars are intimately connected to us. The gold in your jewelry, the platinum in your car's catalytic converter. They were likely born in the heart of a kilonova. These quantum spheres provide a unique testing ground for theoretical physics. At their core, these stars are thought to contain matter at densities greater than that of an atomic nucleus. This ultra-dense environment is a playground for physicists, allowing them to test theories of nuclear physics and quantum mechanics in ways that would be impossible here on Earth. For instance, neutron stars may contain neutrons in a superfluid state, a condition where matter exhibits zero viscosity and can flow without friction. Understanding this state of matter could unlock secrets about the behavior of quantum particles under extreme gravitational and magnetic forces. Moreover, the intense gravity of neutron stars offers a real-world laboratory for Einstein's theory of general relativity. The gravitational field near this star is so strong that it significantly bends the path of light around it. This effect, known as gravitational lensing, which we already talked about, provides astrophysicists with a tool to observe and measure the distortions of spacetime, verifying predictions of general relativity in ways that are not possible in weaker gravitational fields like Earth's. Now, let us fly away from the radiant brilliance of neutron stars, those dazzling remnants of celestial giants, to a realm so vast and empty it defies imagination. A place so eerily desolate, it might seem like a cosmic myth. We are stepping into the heart of cosmic voids, the universe's grand and ominous enigmas, where darkness and mystery reign supreme. Picture an expanse so vast that entire galaxies within it are like distant islands scattered in an ocean of emptiness. This is the realm of cosmic voids, one of the largest structures in the universe. In these staggering stretches of near-nothingness, space itself seems to echo with the silence of absence. They are not just empty space, they are the universe's own deserts, vast and mysterious. While they might seem like vast areas of nothingness, there's actually more to them than meets the eye. Inside these voids, there are some galaxies, though they're few and far between. These galaxies are kind of special because they're often smaller and less developed than the ones we see in busier parts of space. It's like finding a small, quiet town in the middle of a vast desert, far away from the hustle and bustle of big cities. But galaxies aren't the only things in these voids. There's also dark matter, a mysterious kind of matter that we can't see, but know is there because of its gravity. Even though it's invisible, dark matter is really important because it helps shape the structure of the universe, including these big empty voids. These immense interstellar vacuums might also have something called baryonic matter. This is the same stuff that stars, planets, and everything on Earth is made of. In the voids, this matter is spread out like thin, almost invisible threads that stretch across the empty space, connecting the few galaxies that are there. The story of vast cosmic voids begins in the early cosmos. Picture the universe shortly after the Big Bang, a dense, hot soup of particles rapidly expanding. It was during this phase that tiny quantum fluctuations, small differences in density, emerged. As the universe expanded and cooled, these minuscule variations started to play a crucial role. Areas with slightly more matter began to attract more, forming the stars and galaxies we see today, much like snowballs rolling downhill and growing in size. Meanwhile, the regions with less matter, losing in this cosmic tug-of-war, became what we now recognize as cosmic voids. These are not mere empty spaces, but the footprints of the universe's infancy, sculpted by the earliest quantum fluctuations. As we gaze into these voids, we are looking back in time, witnessing the remnants of the universe's explosive birth and its dramatic expansion. The Boots Void is one of the most profound mysteries among these voids. Discovered in 1981 by astronomer Robert Kirshner and his team, the Great Boots Void caught the attention of scientists due to its unusually large empty space. Located in the constellation of Boots, this void is a gigantic expanse of near-nothingness. Imagine an empty sphere in space so vast that it spans approximately 330 million light-years in diameter. To put this in perspective, our Milky Way galaxy is just about 100,000 light-years across. This void contains very few galaxies, around 60, when, based on its volume, thousands would be expected. This scarcity challenges our understanding of the large-scale structure of the universe. To truly grasp the vastness of these cosmic voids, just imagine finding yourself in the middle of an enormous, silent desert under a moonless sky. This desert is so vast that its edges blur into the horizon, with no signs of life or landmarks in sight. The stillness is profound, almost tangible, much like the experience within the cosmic voids of the universe. In this desert, imagine occasionally spotting a faint, distant light, a lantern, perhaps, carried by an unseen traveler. These rare specks of light are akin to the few galaxies that exist within the cosmic voids. They are so isolated and distant from each other that their presence accentuates the vastness and emptiness around them. This immense isolation in the cosmic voids isn't just about the absence of visible objects. It's a reminder of the universe's enormity and the mysteries it contains.